Hello students, so today we are going to discuss about dislocation glide. Now, this dislocation glide is the predominant mechanism of plasticity in metals. So we're looking for plasticity in metals. So dislocation glide is the predominant mechanism behind it. And this is because of the fact that the inherent resistance of the crystal lattice to dislocation motion is small. This is largely due to the fact that the metallic bonding is non-directional. So you can put it in since the metallic bonding is non-directional, so it leads to the resistance of the crystal lattice to dislocation motion is small. So that is why the distortions in the atomic arrangement near the core of the moving dislocations do not produce any large increase in the strain energy as the dislocation moves from one equilibrium position in the lattice to the next. Now, dislocation glide is difficult in ceramics. So, most ceramic fracture before they plastically deform, at least at room temperature. And therefore, bending and complexities in ceramic crystal structure there is a bending and complexity in ceramic crystal structure. Dislocation glide G, let us see, it is difficult in ceramics. It is mainly predominant in metals. Atomic bonding in ceramic is either covalent or ionic or mixture of both. So a dislocation glide also in a covalent material is difficult because it requires breaking and bending of strong directional bonds. So it's difficult in covalently bonded materials. It requires breaking and bending. Since it requires breaking and bending of strong directional bonds. Now, as a consequence, glide plasticity in ceramics like diamond, silicon carbide, and etc. is observed only at extremities of temperature and stress. So, if we increase, so it's not that dislocation glide is not possible. It takes place in silicon carbide, diamond, and even silicon nitride, but they take place at very high temperature or when the stress is only when the dislocation glide can take place. In ionic materials, it is a formation of electrostatic faults which produce a resistance to glides. Ionic materials, we have electrostatic faults which cause a resistance to a dislocation glide. And dislocation glide actually slips along the on a horizontal plane of the simple ionic structure, brings like charged ions into registry. So this brings charged ions. And by bringing the charged ions, what it does is that it does it because to make the atomic arrangements near the dislocation code is half slipped configuration. So it leads to the atomic arrangement near the dislocation code in the half slipped configuration. And it is a high energy slip, and is as possible only those slip systems for which electrostatic faulting is minimized. So it is a requires a high energy slip and will take place only where the electrostatic faulting is minimized. And by minimum electrostatic fault means that it's a 45-degree plane, for example. If it is a 45-degree plane, that means if we have ionic crystals like this, alternate positive and negative ions. So here the dislocation glide is much easier at 45-degree angle compared to the horizontal one. The dislocation glide in ceramics is also difficult due to the complexities in crystal structure. Example, if you take alpha alumina, also called sapphire. The slip system occurs significantly for temperature greater than 900 degrees C. At high temperature ceramics, as previously told, dissolution light is observed. In some ceramics, dissolution light is possible even at room temperature. So at room temperature, those ceramics are basically rock salt structure. You can say that there are some ceramics having the rock salt structure which can show dislocation glide at even room temperature. For others, it is elevated temperature. As the reason that rock salt structured ceramics will show dislocation glide, this is because of the fact that the electrostatic faulting is very less, and almost have no electrostatic faults. And the slip system is basically in rock salt is 110 and 1 part 0 is the slip system. And there are no faults involved in this system. And it is oriented at 45 degrees. So pure zinc crystals exhibit substantial dislocation glide over under the range of temperature. And then now the rule of determining slip systems in crystalline materials is the following: the slip occurs on the plane of the highest packing density, as we all know. The slip is occurring in the plane of highest packing density in the direction of the smallest unit, in the direction of the smallest unit. Now for any cell example, let's say an example like if it is an structure like NaCl, and this is the plane, the highest packing slip at temperature T is relaxed to the expansion of the lattice. So slip at high temperature T is relaxed due to expansion of the lattice.